First of all, I want to thank Jan and Gerhard for bringing this beautiful meeting in this fantastic place together. Even the weather plays along. Perfect. And after these beautiful talks, I want to present some very simple considerations. In particular, I want to talk about the cellular automaton idea in the context of quantum mechanics. And what I want to show for a class of such cellular automata, in particular, arguably the most simple class of such cellular automata, that in the description of them, in the description of their dynamics, quantum mechanical notions come in very natural. I mean, it is almost like the best language to describe these discrete deterministic systems, which a priori have nothing to do with quantum mechanics. And in passing, I will, for the purpose of today, at several points, I want to pay in particular attention to the locality of the description and how this is connected to the linearity of the description. Okay, so now where's the button here? This one here. Okay. Okay, let's see. So by linearity, I mean that the dynamics map states linearly on states. And in quantum mechanics, there are proofs from within quantum mechanics that it has to be so under certain mathematical or more physical assumptions. No, this is the wrong one. Okay, oops. Oh my God. In particular, the most recent one by Jordan says the basic assumption is that if you have a composite system, the parts cannot influence each other without assumption. Then he shows that the theory actually has to be linear in this sense. Now, in the present talk, I want to go away from this, and just linearity will creep in on the side. And what I want to do, I want to start with the description of cellular automata, in particular, based on the idea of discrete deterministic mechanics, which was proposed by Tidili long time ago, and which invokes the existence of a minimal length or time scale. We heard this morning in the lecture of Professor Toft how this can actually be forced on us by describing the process in the vicinity of a black hole. Then I want to use sampling theory as a way to describe this situation. In particular, this will allow us to establish a map between cellular automata, these discrete systems, and a continuum quantum mechanical-like description plus corrections. And the way I do it is based on some very nice work of Heslow in the late 80s, which considers what we usually are used to call the wave function as a composite of a coordinate and momentum, making it a complex quantity in this way as it is indicated here. So what are these cellular automata? I consider a classical cellular automaton which has a denumerable number of degrees of freedom, and they are described by integer valued, let's call them coordinates x and tau, and momenta p and pi, and I separate this tau and pi from x and p because this allows in principle also to describe situations where the time in the system, in the emergent description, if we want, is dynamical. Later on, for my purpose, I will set this to be constant, so the dynamics of this time variable will not really play a role today. And here, just for the notation, alpha enumerates different degrees of freedom and n successive states of this automaton. For the notation, this delta f are these finite difference quantities. And what is very important, because I will talk exclusively for the longest part of my talk only about integer valued quantities. I mean variables, dynamical variables, but also parameters, everything integer valued quantities. Therefore, we have no infinitesimals at our hands, so there are no derivatives anywhere. Everything is discrete to the extremums, I would say. So now, how we describe these things, I postulate, so to speak, out of the blue, but of course it's a way of reverse engineering because I knew somehow what I wanted to get out in the end, so I went backwards, but we can write down this action principle where the action is composed of various parts, and I just want to point out various features of it. This quantity, oh my goodness, let me use this one. Echo, there we are. So there, this quantity is just for abbreviation. But what is important is that this piece here depends quadratically on the dynamical variables. The red quantities are parameters which would describe different systems. So these are constant, in this case, a symmetric matrix and antisymmetric matrix, and here constant parameters. And there is one piece where it eventually could be nonlinear terms or anharmonic terms, that is higher powers, higher polynomials in x and p, these dynamical variables. And we have to talk about this in a little moment. So the action is then written down as here, and the action principle says that it should be stationary under arbitrary variations of this form. Okay, so I have a certain function of a dynamical variable x or p, then the variation is defined in this way, and these delta f's are arbitrary because I have no infinitesimals, so I cannot limit myself to infinitesimal variations, and among the integer valued variations, any one is as good as any other. So this is very different from what we usually do in mechanics or in classical physics, let's say. But now if we do this, and in a moment I show you the equations of motion which come out, what happens is that if you have here an anharmonic term, cubic, quartic, what is convenient or what you would like, then what happens is by this variation principle, we get into trouble because we create more equations of motion than we have variables. So this would be inconsistent, and here we have a first indication that maybe among this class of cellular automata, only the harmonic ones, which involve at most quadratic pieces of the dynamical variables, are consistent. And I will come back to this at various stages and see what we can argue about this. So now let me shortly flash the equations of motion, if I manage this thing here. Oh my goodness, I have difficulty with it. Yeah, this confuses me. I feel already like a robot with all these wires around my head, but a robot which doesn't work well. Okay, where we are. Okay, here you see the equations of motion. In particular, look at these ones for the x and p's. And this look, I mean, at first sight, look completely like Hamilton's equations, except for this possibly dynamical time which enters here. And I introduced here, just to guide the eye, this notation of the dot, which is this finite difference quantity, because it plays the role, in a sense, of the usual time derivative. And this look really deceptively like Hamilton's equations. And now we do a little trick, namely we combine these variables into a complex variable, this I briefly mentioned before, this psi, and it's adjoint. Then we can combine these equations into such an equation, which deceptively, again, looks like a Schrödinger equation, except that everything is discrete, integer valued, and so on and so forth. And of course, this equation and its adjoint. What I did here is to combine this symmetric and antisymmetric matrix into a self-adjoint matrix. And then we see that this plays the role of the would-be Hamiltonian in the Schrödinger equation. So what we get out from this, just a few properties. That's why I say the quantum mechanical analogy creeps in very naturally. First of all, if we have any matrix which commutes with this, so to speak, Hamiltonian, then there exists a discrete conservation law, and you can actually read off from this equation, from this conservation law, what the conserved quantities are. They are of this form. And note here that in distinction to what we would have in quantum mechanics, these are kind of two-point functions because they invoke the value of the dynamical variables at one computer time or clock time and at the next one, or you can take n and n minus 1, depending how you write it. And in particular, if we choose for this operator which commutes with the Hamiltonian, the identity, then we find the analog, so to speak, of the usual wave function normalization. So there is no such thing as psi alpha, where is a summation over alpha implied, which would be the wave function normalization in this cellular automaton, but instead we have this kind of conserved quantity. And we can say that we have a one-to-one correspondence for each of such G's. We have a corresponding conservation law here, which we would have in the corresponding quantum mechanical system. Now, when we came to this problem that the anharmonic equations are not consistent, I mean, if I have nonlinear, higher power nonlinear terms in the action, then of course this was based on the particular way I defined the variation. And I can do, nobody forces me to do this, I can do more generally. I mean, this is what I used. In fact, I can introduce a variation in this way where gamma and m are constant parameters, and I can do it in such a way that if I limit myself to polynomials up to a certain order, which is this n, that this variation exactly has the effect of being a derivative, despite the fact that there's nothing infinitesimal here. It just has the effect, if I apply this variation on such a polynomial, it gives me the corresponding polynomial if I would apply an ordinary derivative to the variable. Okay? And all the terms which would usually be generated by this variation, they cancel by adjusting these coefficients for arbitrary polynomials, but up to a certain power. And this would seem to tell me that I can actually also get a nonlinear equation of this type, I mean of this discrete updating equation. So why not? But now we go to the second part of the talk, because up to now everything was discrete, but we want to make even a closer, that we have seen already the indications how this looks like a little bit quantum mechanical. Now we want to go a little bit closer to quantum mechanics, namely by mapping it onto a continuous system, I mean an invertible map actually. And here we invoke this idea that there is a minimal time, identifying the product of this computer clock variable, which steps up the computer, times this L, this time scale, with the physical time. This naively, doing this in this naive way actually does not work, because in the continuum limit, because we have only integers, if you have two integers and you let them let their position in time go to 0, by letting L go to 0, the derivatives which would come out would diverge. So that does not work. We have to do something a little bit more sophisticated. And this is this idea that we construct a map between these discrete systems and continuous systems, which was, of course, many times advocated by Gerard Torf. And the technique which I will use is actually known to people in information theory, namely that information can at the same time be discrete and continuous. And when you use your cellular phone, you do this all the time because the information is transmitted digitally, but what you hear are analog signals, and vice versa. If you talk to it, it goes into digital coding. And this has been done by Shannon. Actually, the mathematics of this was known much earlier. I mean, was known maybe at least 50 years before, but Shannon drew attention to this in the context of information theory. And what this basic of this idea is this theorem, namely that we consider band-limited functions, functions which have only a finite support. The Fourier transform has only a finite support, let's say, in frequency space. Then if you sample such a function on a set of discrete equidistantly spaced times, then you can reconstruct the continuous functions from these discrete samples identically by using this reconstruction formula. And you notice here that there is this kernel coming in, and you can use actually also other kernels. This is not unique, but what is crucial here is that you have a linear map, namely that these samples are superposed linearly by this summation, and you map this discrete time, so to speak, tentative time on a continuous time now. And so this is one aspect of the linearity. The other one is that the argument of this kernel depends only on the continuous time minus these discrete times. Let's say there you have a lattice in time on these discrete distances. This is very important. If you use any other kernel, you can still have these linearity properties, as I just said. The outcome of this construction is always the same, so it does not depend on this particular form of this reconstruction. And then we apply this to this discrete equation which we had, and lo and behold, we get something like, okay, so I have to hurry a little bit. We get something like the Schrödinger equation, but of course we have to pay a price, namely that there are corrections which depend on this finite time scale. Then we can work out the consequences of this representation, And we find, for example, L-dependent dispersion relations and conservation laws. I will flash it in a moment for you. And now what is nice in this, but also in these results, we can safely take the continuum limit if we want to do that, and we recover the usual quantum mechanical results. So here now the limit can be done smoothly because we mapped the discrete system onto a continuous description. And as I said, if you do this reconstruction in different ways, using different kernels, the equations of motion, I mean, this equation will not change, the conservation laws and the dispersion relation will also not change. But what, of course, changes is how this cutoff implied by this map is implemented. For example, if instead of this sinus cardinalis function, which implements a cutoff on the frequency space of the wave functions which you consider, if instead you use a box function to do this reconstruction, what happens is that the continuous function has to be stepwise constant. So you can have an arbitrary function, but on a fine scale, it has to be stepwise constant. And you can use other kernels. I mean, the people in information business, they have developed all this theory exists. So here, just to flash it at you now, the conservation law, the conserved quantities in the continuum description look like this. And as I said before, t is a continuous variable now. As I said, this is really a two-point function instead of what we would have in quantum mechanics for the corresponding conservation law, where both these arguments would be at the same time. And if L goes to 0 now, everything goes smoothly, we can recover the quantum mechanical results. The dispersion relation for stationary states looks like this, and note in particular that this bound on the frequency spectrum of the wave function translates into a bound of the allowed energy. So there is a maximal energy, which of course goes to infinity when L goes to 0. And the dispersion relation looks like this. This is all one can say. So they're L-dependent corrections to what we would have in the quantum mechanical limit. Okay, now we come back to the question, what goes wrong with these anharmonic cellular automata if we would try to incorporate higher order polynomials into the action? And let's quickly run through this before I come to my conclusions. Namely, what we did was to map these discrete quantities, which describe the dynamics of our system, onto something, let's say, wave function, at the price of having it band limited. And now let's ask, if we have just, for example, a quadratic term here in our equations of motion, what would be the corresponding continuous quantity? Well, this is very easy. We use these properties of these sinus cardinalis functions, which appear in the reconstruction theorem. Namely, they form an orthogonal set. So we can, from the continuous quantity, get back to the discrete quantity. Then we form the square of this quantity. And then we apply the reconstruction theorem again to get this side of what we want to know. And what you find is this. And now you see what goes wrong with these anharmonic systems. Namely, first of all, you see from the last reconstruction, I get here this factor with this summation. So the whole thing is nicely band limit in a consistent way if we would put it into our Schrödinger equation. That is not the problem. But the problem is that this kernel altogether has no intention to produce two delta functions. So this function involves actually these integrations over time. It's not a local quantity, and that would completely change the properties of the equation. It would not be something in any way looking like a Schrödinger equation with anharmonic terms. So let me conclude from this that the anharmonic cellular automata cannot be described in a local continuous way using this approach which I presented. And even more, let's say, qualitatively, there are no L-dependent cellular automaton-based nonlinear Schrödinger equations. So this is just the conclusion for the day. And my summary is here. What we have seen is that there are common aspects between such integer, let's say, natural in that sense, cellular automata and quantum mechanics. This concerns the equations of motion, the conservation laws. Observables I have not talked about, but you can also construct this. What are the observables in this theory, etc. And what is very interesting from this dispersion relation, actually you cannot have an arbitrary Hamiltonian. There is a class, an infinite enumerable class of Hamiltonians which you can have, but they're not completely arbitrary. That is very interesting, but I have no time to talk about it here. In fact, they're completely classified. Then I showed you that we can construct such a map between such discrete deterministic systems and the quantum mechanical description, that it fails for nonlinear cellular automata. And here are just the few, let's say, most important things to do next. One thing you, of course, would like to know how to combine such systems, and in particular combine them in such a way that in the continuum limit you find the usual tensor product structure. And that can be done. A student of mine just finished his thesis and defended it about this, so this can be done. What is completely away here, I did not talk about it all, something which would relate to measurement situations in quantum mechanics. What is the corresponding here? So how do random or non-unitary aspects come into this business? And then, of course, finally, what is still completely missing is the relativistic or quantum field theory extension of that. One would like to do something like this for field theory, but this, as we heard also this morning, very emphasized that this is a very difficult question and it has not been resolved. So I close here. Thank you.